Hi, I'm Sala. In this video, we are going to design a controller for a fast process. We will use internal model control, and our goal will be just keeping the poles at the open loop location because it's fast enough. And in that case, the IMC parameter Q is just constant, the inverse of the dcgain. We'll analyze the setpoint and disturbance response of such a controller. Let's go with the details. This will be the open loop process with poles at 5, and if I plot its open loop step response, I get this step plot, and basically 1.2 is the settling time, and if I had this in closed loop I would be happy. I think the process is fast enough, and I don't wish to accelerate it because I don't wish to spend money in extra actuator power to move it faster. This is perfectly alright for me. With a pole of 5, single pole would have a settling time of 0.8, but a double pole somehow increases settling time 50% extra. But anyway, we are not discussing how to compute the settling time. We see it. We think this response is fast enough, so we wish to design a closed loop controller so that it rejects disturbances with this step response, but of course instead of reaching 3, reaching 1 if the set point is 1. Well, if I don't wish to change the dynamics and I were in open loop, this would be easy. Set point divided by dcgain would give me the step input needed to reach that set point. So in this case, as the dcgain is 3, 1/3 times the set point would give me the open loop control action to reach that set point. But we wish to design a closed loop controller. But then there is the trick of internal model control. The Q parameter of IMC is designed exactly as if we were doing an open loop design. That's the main motivation towards IMC. It's a very simple technique. So good. This means that the EULA parameter, if I were to implement an explicit IMC, would be 1/3, and with this parameter, the closed loop poles would be exactly at the same place than the open loop ones, so we would have finished our exercise if we were in a pen and paper examination. But okay, as we have Matlab, let us analyze the set point and disturbance response of this IMC controller. Let's go. This formula transforms an IMC controller to a standard one, in which input is error. So this is the actual regulator we are designing. As theory predicts, we have integral action, and also predicted by theory there is some cancellation of the plant dynamics, and well, in this case the controller also adds a fast pole, so this transfer function in this second order case can be thought of as a PID controller with a noise filter at 10 radians per second. So let us simulate this controller in closed loop, setpoint response and disturbance response, and extract our own conclusions on how this works. First, let us analyze the setpoint response. This would be the transfer function from setpoint to output. With Matlab's feedback command, we put the direct path gk and the feedback path 1. Okay, this is that t, but I labeled as t1 because, well, it sort of forgot the cancellation or, numerical round of issues. So if I get Matlab to cancel with 0.0003 tolerance, then it cancels these poles and gets this t, which apart from round off stuff, this is 10, then it is this transfer function, divided by 25, numerator and denominator, I get this one, and it's just the same one as the process, but with unit gain instead of gain 3. So this is what we wished. A setpoint response with the same dynamics as the plant, but unit gain. So if we plot the closed loop response and the open loop control divided by 3, we get the same, and it's the 1.2 settling time we were happy with from start. If I compute the transfer function from setpoint to control, k over 1 plus gk, then doing some cancellations, it's exactly q, 0.333. So from the setpoint point of view, IMC gives me the same result as open loop, and this was the theoretical motivation. But let us discuss now the disturbance response. If we consider output disturbance dy, then in this block diagram we can prove that this is the transfer function, and with the feedback command direct path 1, feedback path gk, we obtain this capital S, which is this sensitivity function, and also the transfer function from input disturbance to output is j over 1 plus jk, j times this capital S. So gs will tell me the behavior to input disturbances. So let us plot the step response of capital S and of gs and see what happens. The output disturbance step response. When I get the output step, of course, output increases instantly to 1, but as time elapses, the integral action of the controller makes the final error to go to 0 in that 1.2 settling time we were happy with. So output disturbances will be cancelled to 0 error with this feedback controller IMC. And of course, if I were doing open loop control, if I have no sensor, then output disturbances would never be cancelled. So this is the difference between closed loop IMC, integral action 0 error, and open loop. Now if I plot the step response of GS, this is the effect of an input disturbance in the output. So in open loop is just the transfer function J, because if I have no feedback, I would never realize that the output has drifted, but the internal model control feedback loop with integral actions ends up cancelling in 1.5 seconds the effect of the input disturbance. So this is it. Let us conclude. In this video, we have designed a controller in which the open loop poles are fast, so I don't wish to accelerate the process. In that case, IMC design is straightforward. The Q parameter is the inverse of the gain. Finished. We converted that to a standard regulator, which in this case had a PID form, because the plant was second order, and as it had integral action, we discovered that the settling time to all these three inputs, set point, input and output disturbances, was around 1.5 seconds we were happy with, and of course, due to the integral action of the controller, the error was 0 both in setpoint tracking and in disturbance rejection tasks. So we finish with this. Thanks for watching.